What if I told you that right now, someone on the other side of the world could be watching everything on your screen, recording every password you type, and controlling your computer, and you'd have absolutely no idea it was happening? 800,000 Linux systems are sitting on the internet with their remote access doors wide open, not metaphorically open, literally exposed. No authentication required, no password needed, just a network connection and the right port number, and an attacker can walk straight into these machines. This isn't a zero-day exploit. This isn't a sophisticated hack. This is a misconfiguration so basic, so preventable, that security researchers can barely believe how widespread it's become. And here's what makes this truly alarming. Many of these systems belong to small businesses, educational institutions, and individual developers who have no idea their machines are broadcasting an open invitation to every threat actor scanning the internet right now. Vulnerability centers on X11, the graphical display system that's been part of Linux and Unix systems for nearly 40 years. When X11 is configured to accept network connections without proper authentication, it becomes what researchers call an unauthenticated X11 server. And in February 2024, security firm Cybel published research showing that over 800,000 of these exposed servers were detectable through simple internet scans. Not buried in the dark web, not hidden behind sophisticated networks, just sitting there, visible to anyone running a basic port scan on TCP port 6000. This video is going to show you exactly how this happened, why it's still happening, and most importantly, how to check if your system is one of them. Because if you're running Linux anywhere, especially on a server or development machine, this is not optional knowledge anymore. X11, officially called the X Windows system, has been the backbone of graphical interfaces on Linux and Unix systems since 1984. When developers at MIT created it, they built it with a specific philosophy: everything should work over a network. The idea was brilliant for its time. Your display could be on one machine while your applications ran on another, all communicating seamlessly across a network. X11 uses a client-server model, but it works opposite to what most people expect. The X server runs on your local machine, controlling your keyboard, mouse, and display. Applications are the clients, connecting to that server to draw windows and receive input. Under normal circumstances, when you're just using your desktop Linux system, X11 listens only on a Unix socket, a local connection that stays entirely within your computer. But X11 was designed to also listen on TCP port 6000 for network connections, allowing remote applications to connect to your display. In corporate environments and research institutions, this feature enabled powerful workflows. A developer could run computationally intensive software on a powerful server while viewing and controlling it from their desktop workstation. For decades, this worked reasonably well in controlled, trusted networks where everyone operated behind firewalls and security perimeters. The problem is that X11's network authentication mechanisms were always optional and often disabled for convenience. The assumption was simple: if you're on the network, you're trusted. That assumption is now a catastrophic liability. When security researchers at Cybel began scanning the internet in early 2024, they were looking specifically for X11 servers exposed on public IP addresses. What they found shocked even experienced security professionals. Using Shodan, a search engine that catalogs internet-connected devices, they identified 814,026 unique IP addresses with X11 servers accepting connections on TCP port 6000. These weren't just abandoned test systems or forgotten lab computers. The geographic distribution showed concentrations in the United States, China, Germany, and South Korea, suggesting these were active systems in commercial and educational use. Cybel went further, actually connecting to a sample of these exposed servers to verify they lacked proper authentication. They successfully connected to systems without providing any credentials whatsoever. The researchers demonstrated what an attacker could do on once connected to an unauthenticated X11 server, and the results were devastating. First, an attacker can capture everything you type, including passwords, credit card numbers, and private messages. The X11 protocol includes extensions like Xtest that allow one application to inject keyboard and mouse events into another. This means a remote attacker doesn't just passively monitor your keystrokes, they can actively type commands, click buttons, and control your entire graphical interface as if they were sitting at your keyboard. Second, they can capture screenshots of everything displayed on your screen. Every email you read, every document you open, every website you visit becomes visible to the attacker in real time. Third, and perhaps most dangerous, they can inject commands directly into any application running on that display, including terminal windows, where users might be logged into other systems with elevated privileges. To prove just how easy this exploitation is, researchers conducted a simple test. They connected to an exposed X11 server and used standard X11 tools that come pre-installed on most Linux systems. With a single command, xwd, they captured a complete screenshot of the target's desktop. With another command, xdotool, they injected keystrokes into a running terminal session, executing arbitrary commands with whatever privileges that terminal had. The entire attack required no custom malware, no sophisticated exploit code, just basic utilities that any Linux user can access. And because X11 doesn't log these connections by default, the victim had no record that anyone had been watching. You probably think this only matters if you're running a server in a data center or if you've explicitly enabled remote access features. Here's why that assumption is dangerously wrong. Many Linux users enable X11 network listening without realizing it, often through configuration changes meant to solve unrelated problems. Some desktop environment installers, remote desktop tools, and even Docker configurations can modify your X11 settings to accept network connections. Once enabled, if your system has a public IP address or sits on a network with improperly configured NAT or firewall rules, that X11 port becomes visible to the entire internet. Even systems behind routers can be exposed if UPnP automatically forwards the port or if the router's firewall rules were misconfigured during initial setup. The Cybel research specifically noted that many exposed systems appeared to be development machines and workstations, not just dedicated servers, suggesting users had unintentionally exposed their personal computers. Automated scanning tools constantly sweep the entire IPv4 address space looking for vulnerable services. When Shodan and similar platforms index an exposed X11 server, that information becomes searchable by anyone, including attackers. Cybercriminal forums actively share lists of vulnerable systems, and once your IP address appears on those lists, you become a target. The attack surface isn't limited to sophisticated nation-state actors. Script kiddies with minimal technical knowledge can download pre-built tools that automatically find and exploit exposed X11 servers. The regulatory implications of this exposure are significant, particularly for organizations handling sensitive data. Under GDPR, which applies to any organization processing data of European citizens, exposing personal information through negligent security configurations constitutes a breach of the security principle outlined in Article 32. Thus, regulation requires appropriate technical and organizational measures to protect personal data and an unauthenticated network service that allows arbitrary access to screen contents would fail this standard. In the United States, healthcare organizations using exposed Linux systems could violate HIPAA if patient information becomes viewable through these sessions. The UK's Information Commissioner's Office has repeatedly emphasized that misconfiguration vulnerabilities, even when not actively exploited, represent a failure of data protection obligations. Security researcher Christian Erik Hermansen, who has extensively documented X11 security issues, described exposed X servers as one of the oldest and most persistent security anti-patterns in Unix administration. The SANS Institute, a leading cybersecurity training organization, has included X11 security misconfigurations in its list of critical controls since the early 2000s. Germany's Federal Office for Information Security, the BSI, published specific warnings about X11 exposure in their technical guidelines for secure Linux deployment. These aren't fringe concerns from paranoid security consultants. These are mainstream security organizations recognizing that a 4-decade-old design assumption that networks are trusted has become fundamentally incompatible with internet-connected computing. The human impact becomes clear when you consider realistic scenarios. Imagine a medical researcher analyzing patient data on a Linux workstation in a hospital. They're viewing spreadsheets with names, diagnoses, and treatment outcomes. If their X11 server is exposed, an attacker halfway around the world can capture screenshots of every patient record that crosses their screen, all without triggering any obvious alerts or warnings. The researcher has no idea their display is being monitored. Now, consider a software developer working for a financial services company, writing code that handles transaction processing. They're testing the system using real database credentials visible in their terminal window. An exposed X11 server means those credentials, which might provide access to millions of customer accounts, are being broadcast to anyone who connects. Or, picture a journalist in a country with limited press freedom communicating with confidential sources about government corruption. Their X11 session captures the names, contact information, and conversation contents before any end-to-end encryption can protect those communications. In each case, the victim has no warning, no notification, and often no way of knowing they've been compromised until damage has already occurred. The exposure is silent, invisible, and complete. The Linux community's response to the Cybel findings was swift, but revealed how fragmented security practices have become. Major distributions like Ubuntu, Fedora, and Debian have disabled X11 network listening by default for over a decade, meaning fresh installations don't have this vulnerability out of the box. However, many users and organizations are running older systems, using customized configurations, or have explicitly enabled network features for legitimate reasons without implementing proper security controls. The X.org Foundation, which maintains the X11 implementation used by most Linux distributions, has consistently recommended using SSH-X11 forwarding instead of direct TCP connections for remote display scenarios. SSH forwarding encrypts the connection and integrates with SSH's authentication mechanisms, providing the remote display functionality without exposing an unauthenticated service. Despite these recommendations being available for over 20 years, implementation remains inconsistent. What's particularly concerning is what researchers found even on systems that attempted to implement security. X11 does support authentication through mechanisms like MIT, Magic Cookie 1, and XDM Authorization 1, but these were designed for the threat model of 1980s campus networks, not the modern internet. The Magic Cookie system, the most commonly used authentication method when any is used at all, relies on a random 128-bit value stored in a file called .x authority in the user's home directory. Any application that can read this file can connect to the X server. If an attacker gains any level of access to the system through another vulnerability, or if the home directory is accessible through a misconfigured file share, the authentication becomes meaningless. It's the equivalent of protecting your entire digital life with a key that's left under the doormat. Even after the February 2024 disclosure, follow-up scans conducted by independent researchers in subsequent months showed the number of exposed systems declining only slowly, suggesting many administrators either weren't aware of the issue or didn't know how to remediate it. The systems that remained exposed included IP addresses registered to universities, web hosting providers, cloud infrastructure platforms, and telecommunications companies. These aren't fly-by-night operations. These are organizations with IT departments and security policies, yet they're running systems with a configuration vulnerability that's been understood for decades. So what can you actually do about this? The first and most critical step is to check whether your system is listening for X11 connections on a network interface. Open a terminal and run this command, netstat-tun pipegrep 6000. If you see a line that shows 0.0.0.0 6000, or your machine's IP address followed by INS 6000, your X11 server is accepting network connections. You can also use SSTUL pipegrep 6000 on newer systems. If those commands show X11 listening on anything other than localhost or show nothing at all, you're already protected. If they do show network listening, you need to disable it immediately. For most desktop Linux distributions, X11 network listening is controlled by Display Manager settings. If you're using GDM, which is the default on Ubuntu and Fedora with GNOME, edit the file /etc/gdm3/custom.conf or /etc/gdm/custom.conf and add this line under the security section, disallow TCP equals true. Then restart your display manager or reboot. For systems using LightDM, edit /etc/lightdm/lightdm.conf and ensure the line X server allow TCP equals false is present under the seat asterisk section. If you're running a server without a graphical interface but X11 is somehow installed and listening, the solution is even simpler. Use your firewall to block incoming connections on port 6000. With iptables, run sudo iptables, input p, TCP dport 6000j, drop. With firewall, run sudo firewall cmd permanent add rich rule equals quote rule, family equals IPv4 port protocol equals TCP port equals 6000 drop quote, and then reload with sudo firewall cmd reload. And these commands prevent any external connections to the X11 port even if the service is running. For organizations managing multiple Linux systems, implement network-level controls as well. Configure your border firewall to drop any inbound connections attempting to reach TCP port 6000 on any internal IP address. This provides defense in depth, protecting even misconfigured systems from internet-based attacks. If you legitimately need remote graphical access to a Linux system, never expose X11 directly. Instead, use SSH with X11 forwarding enabled, which you can do by connecting with SSHX username at hostname. The X flag tells SSH to securely tunnel the X11 protocol through the encrypted SSH connection. On the server side, ensure the file /etc/ssh/sshd_config has X11 forwarding yes set. This gives you all the functionality of remote X11 without any of the security nightmares of an exposed X server. Alternatively, for full desktop remote access, use VNC or RDP solutions that implement proper authentication and encryption, such as Tiger VNC with TLS or XRDP configured with certificate-based security. Your operating system isn't just a tool you use anymore. It's a continuously connected system that, if misconfigured, actively broadcast your private information to anyone with the technical knowledge to look for it. 40 years ago, when X11 was designed, the assumption that networks were trusted made sense. Today, that assumption can cost you everything stored on your computer, everything displayed on your screen, and everything typed on your keyboard. The 800,000 systems Cybel found aren't theoretical vulnerabilities in academic papers. They're real computers, used by real people, exposed right now. Run those commands. Check your system. If you manage Linux systems professionally, or know someone who does, share this information with them. The security community has been trying to eliminate this vulnerability for 2 decades, but it persists because awareness hasn't reached the people who need it most. Your data is only as secure as your weakest configuration. Don't let a 40-year-old design assumption be the thing that compromises everything you've built.